Hey everyone, and welcome back to The Explainer. Today we are stepping way outside the realm of everyday standard code and diving into something honestly kind of mind-bending. We are looking at a highly abstract theoretical Python architecture. We're essentially looking at the blueprint for a digital universe, constructed entirely through code. We're going to examine the foundational layers, the execution runners, and just the sheer massive scale of the matrices designed in these source documents. If you love seeing how structural code can model massive theoretical concepts, you are absolutely in the right place. Here is our roadmap for today. Foundations of unified memory, the interference discovery engine, scaling the spectrum matrix, harmonic and physics registries, and finally, the grand unified system. All right, part 1, foundations of unified memory. So before you can build a whole cosmos, you obviously need a place to store its data, right? We're looking at the core Python classes drawn straight from our source material here: comprehensive unified memory and extended unified memory. In the code, the very first action taken is instantiating the matrix extension using that extended unified memory class. And what's really crucial to understand here is that this foundational layer immediately imports standard Python modules, like math. From line 1, this memory isn't just storing static text, it's gearing up for some incredibly heavy numeric matrix-based calculations. 200. In this architecture, this exact figure represents the strictly verified nodes that make up the static memory registry layer. Just nodes 1 through 200. You can kind of think of this as the bedrock or the tightly controlled foundation of a massive skyscraper. Before generating anything complex at all, the system relies on these 200 verified points of memory as its absolute source of truth. Moving right along to part 2, the interference discovery engine. Once we have those 200 static nodes locked in, we actually need a way to process them, so the code brings in the heavy hitters. The discovery engine class is powered by the math module and the NumPy library. Now, the second you see NumPy appear in a script like this, you just know this architecture means business. It is fully preparing to handle complex, multidimensional arrays. The engine is actively hunting for interference patterns, relying on highly optimized C-based math to calculate all these complex interactions across the matrix. Which brings us to part 3, scaling the spectrum matrix. Because, let's be real, a universe of just 200 nodes isn't much of a universe, is it? We're about to observe a massive jump in structural scale here. We basically leave behind that trusted, verified static memory registry layer and enter what's called the high-density generative spectrum matrix. This is a huge architectural leap, where the system stops just holding data and actually starts dynamically generating it. And here is the awe-inspiring metric of that leap: 100,000 nodes. Yeah, you heard that right. This is the designated size for the infinite unified spectrum matrix class. We've scaled all the way from 200 foundational nodes up to a 100,000 node matrix. Handling a generative spectrum of this magnitude requires immense computational overhead. Let's just say you better hope whoever runs this script has plenty of RAM, but it perfectly explains why NumPy had to be imported in the previous layer. But a system generating 100,000 nodes of high-density data presents a pretty glaring problem. How on earth do we know any of it is actually accurate? How do these massive matrices corroborate all this generated data? That is the pivotal question that pushes us out of raw memory and into the actual execution and verification phases. Part 4, harmonic and physics registries. So, to answer that data accuracy question, the architecture introduces some very strict execution runners. First up, the unified harmonic registry is initialized to act as the memory bank containing those original 200 verified nodes. This keeps the massive system grounded. Next, the physics mechanics registry boots up to handle the high-fidelity mechanics and system reports. And finally, parallel reaction matrix circuits are initialized to run the actual verifications. Everything is tightly compartmentalized to ensure total data integrity. And finally, part 5, the grand unified system. With our memory stored, our engines running, and verification in place, we've basically reached the summit. Let's just walk through the literal execution block sequence defined in the main runners. Step 1, initialize the unified harmonic registry for data corroboration. Step 2, boot up that physics mechanics registry. Step 3, initialize the complete universal system registry via the cosmological unified matrix. And finally, step 4, run the absolute overarching engine, the grand unified system matrix. This cascading sequence ensures absolute verification happens before the grand engine takes total control. Okay, I really have to pause here and point out the grandiose, highly conceptual naming conventions happening in this code. I mean, in standard software development, you're usually looking at classes named data processor or app controller. But here, we have the cosmological unified matrix and the grand unified system matrix. Clearly, the architect of this code had a bit of a god complex. But seriously, though, it really speaks to the massive, almost unbelievable ambition of the theoretical modeling taking place in these scripts. This breakdown summarizes the taxonomy of our advanced verification matrices, and I really want you to notice the required modules here. Across the board, they rely on JSON and math. The JSON module is absolutely critical. It tells us that these vast universal registries are likely parsing and passing their complex, multi-layered data in JSON format, which is literally perfect for this kind of hierarchical information. You'll also see the harmonic registry utilizes the sys module, proving it interacts directly with the Python interpreter or the operating system itself to manage these massive system-level executions. To really bring this code to life, let's look at what actually happens when you execute the main block. The terminal literally spits out, initializing parallel reaction matrix circuits. This is the exact moment the static code wakes up. You can almost visualize the entire system lighting up as the verification runners begin to ping those 100,000 generated nodes, aggressively cross-referencing every single one of them with the 200 foundational static registries. Which leaves us with a pretty profound final thought. We just traced this blueprint all the way from a tiny foundational 200-node memory bank through some intense NumPy-powered engines all the way up to a 100,000-node grand unified system matrix. Consider the sheer scale of the data architecture we just unpacked today. What limitless theoretical applications could possibly be modeled if this type of cosmological matrix were fully realized and populated with real-world data? It's a wildly fascinating look at how code structure itself can mimic the complexity of a universe. Thank you so much for joining me today. Keep questioning everything, and I'll see you in the next explainer.